Okay, so now we are going to look at using the cosine similarity measure to compute the network level similarity, and for that we need to have an understanding of what an eigenvalue is as well as an eigenvector. Alright, so if you consider a square matrix like this is a 2 by 2 matrix. So if A is a square matrix of dimension n, as n by n matrix, now we if we can find a scalar value, scalar means some number, some real number, and we can call it as the eigenvalue of this matrix A if we can find a non-zero column vector x such that Ax equals lambda x. So if we can find such a lambda and x, then we can call the column vector x as the eigenvector of the adjacent of the matrix A corresponding to the scalar value, which is called eigenvalue now, del and lambda. What all these things mean. So if A is the matrix, square matrix, for example 3, 2, 3, negative 2, I want to find a column vector say, to 1 for a given lambda 4, such that if I multiply A by this column vector, I get lambda times the column vector. Okay. So if this equality is true, then we can say this 4 is the eigenvalue and the corresponding column vector to 1 is called the eigenvector. Okay. So again, let me repeat. So if you're given a square matrix, say in this case a 2 by 2 matrix, now if you can find a scalar value, say 4, and corresponding column vector say 2, 1, such that if I multiply this matrix by this column vector 2, 1, I get same as the scalar multiplied by the column vector. If this equality is true, then this 4 is called the eigenvalue corresponding to this column vector, which is called the eigenvector. So let's see if it is true. So this is a 2 by 2 matrix and this is a 2 by 1 matrix. So you should be able to multiply the number of columns in the first matrix is equal to the number of rows in the second matrix. So you should be able to multiply, and it's going to be 2 row 1 column matrix. So that's what it is, 2 row 1 column. So it's going to be 3 times 2 plus 2 times 1 plus, and this one is 3 times 2 plus negative 2 times 1. So that's going to be what is this, 6 plus 2, which is 8, then 6 minus 2, which is 4, so 8, 4. Now here you have 4 times 2 is 8, 4 times 1 is 4, so 8, 4. So this equality is indeed true. So we can say this 4 is eigenvalue and the corresponding column vector to 1 is eigenvector. Now how many eigenvalues and eigenvector you are going to have for a square matrix? So it depends on the dimension. So this is a 2 by 2 square matrix. So you're going to have 2 eigenvalues and the corresponding 2 eigenvectors. Okay. So it's a property. So if we have an n by n matrix, you're going to have n eigenvalues and each such eigenvalue will have a corresponding eigenvector. Alright, so now if we have a graph, we can also get the eigenvalues and eigenvectors for the graph. Now we can use the adjacency matrix or the adjacency list to get the eigenvalues and eigenvectors. So in this module I have posted a jar file for you guys to use an adjacency matrix representation to generate the eigenvalues and eigenvectors for the corresponding matrix. So you can generate the eigenvalues and eigenvectors for the adjacency matrix as well as for the pairwise cosine similarity matrix that we saw earlier. So let us first see for an adjacency matrix, you're going to have either 0 or 1 as the entries, and so again you know that 1 means there's an edge between the corresponding 2 vertices and 0 means they don't have an edge between them. So for example 1 has an edge to 2, 3, 4 and 5, so you have 1s, and then 1 doesn't have an edge to 6, 7, 8 or 9 or 10. So you don't have 1, you have zeros. And it's a symmetric matrix, so if you have for 1, 0, 1, 1, 1, 1, 0, zeros. For column, we also have 0, 1, 1, 1, 1, and all the zeros. So you can come up with adjacency matrix. So you can save it as a text file and feed into the adjacency matrix eigenvalue program. Okay, so let me show that here for you. So this is my adjacency matrix. So I have given you a jar file corresponding to adjacency matrix EEC. So that's the jar file you're going to use now. Load the it's always run the executable. Now load the adjacency matrix file. So I have it saving as this, and so you're going to have 10. So this is a 10 by 10 matrix because that's the number of vertices. So now you're going to have 10 eigenvalues, and for each eigenvalue, starting from the smallest eigenvalue to the largest, you're going to have the corresponding eigenvectors. Okay. So the entries in the eigenvectors will actually have some relation with the vertices here. So the vertices are numbered 1 through 10, so that's why the eigenvector entry is also numbered 1 through 10. Now if you notice here, if you pass in the adjacency matrix for this graph as input, as we just did, the eigenvector corresponding to the largest eigenvalue. So this is the largest eigenvalue among all the eigenvalues. So this is actually listed in the increasing order of the eigenvalues. So the largest eigenvalue is 3.389. Okay, and so the largest eigenvalue has a name. It is called the principal eigenvalue. Now the entries corresponding in the eigenvector for the principal eigenvalue actually are the eigenvector centrality values. So the eigenvector is called the principal eigenvector corresponding to the principal eigenvalue, and the entries in the principal eigenvector actually correspond to the eigenvector centrality of the vertices. Okay. So 0.474 is the eigenvector centrality for vertex 1, 0.4568 is for vertex 2, and so on. And you can see 1, 2, and actually 3 have a larger eigenvector centrality because they have several neighbors and their neighbors also have several neighbors. So as you remember, eigenvector centrality is a measure of the degree of a vertex as well as the degree of its neighbors. So 9 and 10 have a low eigenvector centrality because they have a degree 1. They are attached to node 5, which has also reasonably not very high but moderate level of eigenvector centrality. So 9 and 10 have a very low eigenvector centrality. Now, so you can save this entry as a text file in your code and in your computer, and you can analyze further. Now, what we are going to do is, so what I just said is we can save this as a text file and do whatever processing if you want to. Now what we are going to do is this. We are going to use the pairwise cosine similarity matrix we came up with in the previous video and use that as a basis to compute what is called a network level similarity. Okay. Now so this is the pairwise cosine similarity matrix. Now you see here in the pairwise cosine similarity matrix, the entries are of course between 0 and 1, and now if you have all the entries other than the diagonal to be 1, then actually that would correspond to what is called a complete graph, because every vertex then would be considered to have an edge to every other vertex. So what I mean is, if other than the diagonal, which is always 0, if you have all ones, the rest of the entries, the corresponding graph could be called a complete graph. That means every vertex has an edge to every other vertex. Now if you compute the principal eigenvalue for such a matrix, you're going to get an answer corresponding to the number of vertices. Okay, so 7 is the largest principal eigenvalue, okay, for such a complete graph. Okay, so we'll stop with this video and do one more video on this.